Your name.
All right. So welcome back. So can y'all hear me okay?
Yeah, I can hear you.
All right, thank you.
You're welcome.
All right, Lauren, thanks for letting me know. So I'm going to cover 10.6 tonight. So just so you know, try to keep up because they're going to start coming fast and quick next week. So all of these things are going to be due by the end of next week because we're looking at a test in 2 weeks from today. All right, let's see. All right, well, give me a minute to get things set up. So before we get started, anybody got any questions, comments? So as I had said, we're looking at a test in about 2 weeks. It's going to be on Respondish as usual during the class time. I'll try to open it up early in the 020 so that way, you have a little bit of flexibility. So we are going to head on and look at 10.6 and let's see. All right. So 10.6 deals with this thing called odds. Now, when we're talking about odds, we're talking about the relationships of winners to losers or losers to winners. Probability is slightly different, but it uses the same information. So what I have on here is a little bag of items. And I'm going to try to fix this to make it a little bit more understandable. I'll come back and fix that in a minute when I do this. Okay. It's just bugging me the way they do that. But anyway, so I want to look at this one right here. All right. So in this bag of marbles, we got 2 reds and 4 blue.
No.
So for every 2, I'll tell you what, let's back up a second. Let's talk about the probability of red first, since we already understand what probability is a bit. Okay, so in this bag of marbles, there are 1, 2, 3, 4, 5, 6 marbles. And how many of those are red? How many are red out of these? Go away. 2 out of 6. 2/6 probability of picking red. Now, we always want to simplify our probability, so we have a 1/3 chance if we reach in that bag blindly and pull out a marble, we have a 1/3 probability that we will get a red marble. And that's what that means right there. There's our 1/3 probability for red.
Mm-hmm.
Now, odds are slightly different. We don't use the total, all right? we use the fact that odds let me go ahead. So this is odds for or odds in favor of getting red. So in this bag, there are 2 red and 4 blue. Now, we always want to simplify our proportions. We don't want to keep a common factor. So we're going to do the same thing we did with that fraction up there. So our odds for red are 1 to 4.
Mhm.
So for every, oops, I'm sorry. How did I do that? I was hitting on all cylinders here tonight. I'll tell you what, let me slightly different here. So what's the probability of not red? In other words, blue. What's the probability of blue? There's how many blue?
4
4.
or 6.
Out of the 6. And that simplifies to 2/3.
Third.
And that makes sense because 1 and 2 give us 3, or 3
Mhm.
over 3, which is 1. And that should happen. The probability of getting red and not red, and this could be any event, it's just not just the colored marbles. Anytime we do this, we can find that the numerators will add up to give us that denominator of these 2 events, the probability of an event occurring and it not occurring. So this number up here in the probability of success is called A, and here we call that B because it's the numerator of not our event, not red. So odds in favor, or odds for, is 1 to 3. I'm sorry, 1 to 2. 1 to 2. So for every 3 marbles, 1 is red, 2 are blue. That's how odds work. They're derived from the numerators of the probabilities. And just notice that these numbers, it's no mistake that the 1 and 2 then add back up to 3.
Mhm.
So remember those things. Here's the formal definition here now. So odds against an event, and this is usually sporting odds, uses odds against. It's the ratio of losses to winners. So that's why we say B to A. So if we said odds against red, then we would just turn them around. And that's one that they usually use in gambling. Odds in favor is equal to A to B. You just turn them around. So in other words, for odds in favor, the numerator of your probability of success comes first, and the numerator for your probability of failure comes second. They're just reciprocals of one another. All right, I'm gonna work one of these, and then I'm gonna go over to Alex and do one of those, since those are kind of nicer and more helpful to students. All right, So if we have the probability of a horse winning a race is 1/12, then find the odds against the horse winning. All right. So we got odds in favor. I'm sorry, probability of horse winning. So probability of losing is what? What would that be? What would the probability of losing be? If one of them is a winner, then how many of them are losers?
11.
11 over 12. Again, you're using the complement rule, but most people don't like to think about the complement rule just because it makes it even more nebulous to understand, but that's what you're using. The easy way to find this is 1 from 12 gives you the 11. 11 from 12 gives you the 1. So now this is our A, and this is our B. So they want odds against. So then that's going to be 11-1. And those are the kind of things you would see if you do horse gambling, because 11-1. Hey, this horse is 11-1. Well, what does that mean? Most people don't want to think about that, but that means that for 12 runnings of that race, you'll have the horse will lose 11 times and win once. So just to show you, odds in favor would be 1-11. And that doesn't sound nearly as nice and enticing, but that's what it means. They both mean the same thing. One winner for every 11 losers in the running of that race. So I'll do this one and I'm going to go over and hit some Alex stuff. So we got 3. Thirteenths of getting an A. So what's the probability of not getting an A?
Ten.
3 from 13, so it'd be 10/13. So the numerator for the success of getting an A in this case is our A. All right, so there's our A and there's our B. So odds in favor now is A to B, which is 3 to 10. So for every 13 people, 3 get an A, 10 don't get an A. All right. Let me show you one more thing, and like I said, we'll hit a problem over in a couple problems over in Alex. Now, we can reconstitute probability as such. All right. It doesn't matter whether we've got A to B or B to A. If we've got odds in favor or odds against, we've got the two numbers that we need. We just got to put them in the right spot. Now the denominator is the easy because you're just adding them up. All right. And if we want the probability of an event occurring, then we use the A. If we have probability of not the event, then we use the B. So we got here the odds in favor of a mouse being eaten by a snake in the wild is 9-2. Odds in favor. So A is equal to B is equal to 2. My question. So now we're just going to follow this formula because will be eaten is going to be A, which is 9, over A plus B. So the probability of being eaten is 9/11. And so the probability of not eat is going to be similar, except we're going to use the B in the numerator. So 2/11. And again, you can see the 2 and the 9 add up to give us the 11, as we should get with the complement rule. They should add up to get that denominator, because that way they add up to be 1. All right, any questions? We'll go over and look at a couple of Alex problems. Okay. So finding odds in favor and against, it could be either one. We got to pay attention to what they're asking. So Pablo is playing a carnival game. He is blindfolded while he throws a dart at a board of 12 balloons as shown below. Now we're assuming that he hits it. Each balloon is labeled S for small, M for medium, L for large, and XL for extra large. So the board has 3 small balloons, 5 medium balloons, 2 large balloons, and 2 extra large balloons. He hits one of the balloons at random and wins a stuffed animal of that prize. So we want to find 2 things. Find the odds against Pablo winning a medium stuffed animal, and the key thing is here, medium, and then find the odds in favor of that same median. Now, in order to get probability, in order to get odds, we need the probability of win and lose. All right. So the probability of winning, and y'all folks should be able to tell me this. So what would the probability of winning a medium animal be? I'm sorry, balloon. I don't know what you get, but you get medium stuffed animal if you hit one of these 1, 2, 3, 4, 5. So what would the probability be for medium?
5/12.
Good, good. 5/12, because there are 5 that are medium and there are 12 balloons total. They give you both those numbers, and then you can also see it in the description. Now, can this be simplified any?
No.
No, there's no common factor between 5 and 12. All right. But we need the probability of not winning or losing. Probability not win. So how can we find that? We can use the complement rule, and I've got that in my notes, but most people don't like thinking about the complement rule. But this is what happens is the probability of winning and not winning have to add up to 1. So in order to get to 1, we need to know the number that's missing from 12. So if we take 5 from 12, 12 minus 5, we get 7. And now 5 and 7 give us 12. 12/12 is 1. So now A is equal to 5 because it's the numerator for winning, and B is equal to 7 because it's the numerator for not winning. All right. So now odds against, we need odds against. Let's put a little reminder here. Odds against is B to A. So in this case, what would we have? What's B? 7 to 5. 7 to 5. And that's what's going to go here. 7 to 5. So that means 7 losers, 5 winners on that board. And they both add up to 12, which that's because there's 12 balloons. Odds in favor is A to B. So that would be 5 to 7. Just turn them around. Okay. Any questions? All right, let's see what else they got over there we can work on. I don't know if I want to do this one or not. Let's see. Yeah, this is probably a good one because this one is in there, and I don't really like the way they give you both the probability and the odds as fractions, but we got to live with that. They do give you a possibility of writing it with a colon, so that's what I choose to do. I don't want to mistake my probabilities for odds. All right, so Christine is playing a role-playing game with her friends. She's going to roll dice to determine if her character casts a spell. Odds in favor of her casting a spell is 11 to 8. 11 to 8. That's my preferred way of writing odds because this right here makes it look as a fraction, which is valid, but I can say it is. It just can be confusing in some cases. So I try to keep my things separate by writing the odds always with the colon. All right. So find the probability of her casting that spell. All right, now this is our A. I'm sorry, yeah, A. And this is our B. So our probability is going to be as such. So success. So it's going to be A over A plus B. So what will that be in our case? The numerator is the easy part because it's always the two numbers added up. But we want the probability of her casting the spell. In other words, we want the probability of success. So we need A, and A is what? 11, right? So 11 over 19. Okay, any questions about that?
No.
All right, now this one, it's not just a regurgitation like that other one was where you just turn them around. This is actually giving you something else. It's giving you the probability of choosing a green block. All right, so we want to find the probability. I'm just going to write out the probability So now for these, when we go into the odds, we got to have the probability of not getting green. All right, so what's the probability of not green? 6 from 17.
$11.
Yep. So it's 11 over 17 now. And they should always have that same denominator. All right, so A is 6, B is 17. All right, so odds against B to A. So our B is 17 and A is 6. So the odds against are 17 to 6. In other words, 17 losers, 6 winners. All right. So let's see what else they got out here. All right. I'm gonna look at this one and see if I want to go. If I get time, I may come back to this one. All right, we'll do this one because the cards is nice and visual, and I like these examples when we can actually see them. All right. So odds in favor of drawing a spade. So we got to find, when we want odds, we got to have the probability of getting a spade and not getting a spade.
Would it be 13 over 52?
Let's see. You're probably right. It's definitely 52 in the denominator. Oops. And how many spades are there?
Somebody going to 13.
13. And that simplifies down to actually
One.
1/4. So 1/4 of the deck are spades. And this would apply if it was clubs, diamonds, or hearts as well. All right. So here's the part where people get hung up. So pay attention. We need the probability of not spade. We could go through there and figure out all the ones that are not spade. And then it would be something we have to simplify, but we can do it easy way using the complement rule. So 1 from 4, so 4 minus 1 is equal to 3. So then the probability of not a spade is 3/4 because there's 3 of those suits that are not spades. So A is equal to 1, B is equal to 3. So they want odds in favor of a spade, and odds in favor or odds for is A to B, so 1 to 3. So the next one, it's different, so pay attention. They're not always asking about the same thing. They're usually the first problem they give you, it'll be the simple variety where it'll just be odds in favor and odds against of the same event. But these are different. So we got to do the same thing that we did, except now we got to do it for a king.
So would it be 4 over 52?
Look, I think you're right. But let's go ahead. Let me go ahead and so 4 kings out of 52, and we'd be better off go ahead and simplifying this. So that's 1/13.
Over 13.
1 over 13. 4 goes into 52 13 times and into itself once. So now 13 minus 1 gives us the 12 for the numerator of not a king. So 12 of the 13, and you can see it in any one of these suits. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So 12 out of each one of those suits are not kings. So then we can do the same thing here. A is equal to 1, B is equal to 12. So they want odds against. Odds against is B to A. So 12 to 1. And it's no accident, again, that the 12 and the 1 add up to get you back to your original denominator. All right, any questions? That's going to probably do it for odds, and we're going to get to this thing called expectation here now. So let's find us another problem. All right. So expected value, it's something that you can't really put into a formula that really makes a whole lot of sense. It just looks very, very menacing if you do, because you'll notice here that they give that the expected value is equal to x1 times the probability of x1 plus x2 times the probability of x2 plus ... all the way out. So however many situations you have, you're going to just take your outcome, which you get when you win, times that probability, and you do that for all of your possible outcomes, and then you add them up. So I'm going to do those in Alex. That's an Alex, the problem over there. The first one is expectation, but it's a very simple synopsis of it. It's just to show you that you use past information in order to get an expectation of what is to come. It's like with boy and girl births. Let's just say in our area that it's exactly a one-to-one relationship. In other words, 50% are boys and 50% are girls. So with that, the next 100 babies on board, you expect about half of them, 50 of them to be girls and 50 of them to be boys. It may not be exact, but it's a prediction based upon past events. So what we're going to do here is a very, very simple expectation. So why don't somebody read that for me, please? My voice is starting to go. Who wants to read that? Save their poor teacher's voice.
Mrs. Flores is a librarian at the East Side Library and examining a sample of the library's book collection. She found the following: 864 books, no damage, 174 books had minor damage, and 43 had major damage. Based on the sample of 44,000 books in the collection, should Ms. Flores expect to have no damage? Round your answer to the nearest whole number. Do not round.
Yeah, don't round in between. In other words, when you do calculation, as we start to get into the what's called statistics, you don't round things off until you get to the end. All right. So I'm going to say proportion of books with no damage.
Oh, and I kept going up.
All right. So there's 864 books that are not damaged. Out of how many? See that right there? That's how many books she's looked at. See? And examining a random sample. In other words, somebody went out there and just picked books at random to make sure that it represented the entire 44,000. And then this came out to be, and what we got to do is we got to add up all those. So 1,080. So let's see what that proportion comes out to. So 0.08, I'm sorry, 0.8. And if we wanted to think about that in terms of percent, we'd multiply it by 100. So about 80% we can expect to have no damage. All right. So what I'm going to do is I'm just going to go to these 44,000 and take 80% of it, or using the proportion. All right. Percents don't do math very well. They're for expressing ideas. So there we got 35,200 books we could expect to not have any damage. So that's an expectation. That's an expectation. In other words, that's what we would expect to happen. It may not be exact, but more or less, that's what expectation is. It tells us what we can expect to happen over large numbers, and in this case, of the 44,000, 80% of them, 35,200. All right, let's see now one that's a little bit more like expectation here. All right. All right, Josh has a deck of 10 cards numbered 1 through 10. He is playing a game of chance. So 1 through 10. Josh chooses one card from the deck at random. He wins a money amount equal to the value of the card if it's numbered odd. If it's even, he loses $4.20. So what I need to do is I got to make myself a little chart here. These work very charts. So we got 1, 2, 3, 4. I'm gonna come back in and put the lines in a minute. All right. So now what I'm going to put on this line here, this row, I'm going to call it X, and this is what we call the outcome. In other words, when we get 1, so it's called X because it changes depending on which one of these 10 numbers it falls on. And then this is the probability of each one of those. Now, thankfully, they tell us so it's a fair game. In other words, there's 10 of them. If you're picking at random, you got 1 out of 10th chance of getting either one of those cards. So I'm going to put this part first. So each one of these is going to be 1/10. I probably should have done a shorter one just for brevity's sake, but we'll get through it. The one I did today in class, it had like 6. Made it a lot easier for the presentation. All right, now, so what happens when he gets an odd number? He wins an amount of money equal to the value of the cards if it's odd. So in other words, he's going to get $1. He's going to get $3. He's going to get $5. All right. Now, what happens on this one? It's going to be negative. I should put a little bit more room, but it's 4.2, 4.2, and it's negative because he's losing. But each one of these is a 4.2 negative. $4.20. I really wish that they didn't use the cents on each of these, but wish it was just like something like -4. What make it a lot easier. Now, remember this crazy formula over here that define the expected value. We're going to take the X times the probability of X of each one, and then we're going to add them up. All right, now here's what we got to realize with these. When we're multiplying 1 times 1/10, we get 1/10. So this is X times probability of X. So 1 times 1/10 is 1/10. Now, just to show you what happens on the rest of these, I'm going to come over here. If we take -$4.20 and we're multiplying it times 1/10, then the denominator of this is 1. So what you're multiplying only multiplies the numerator. So this is -4.2 over 10. And then the same thing here. 3 times 1 is 3/10. -4.2 . 4.2 . 4.2 . 4.2 . 4.2 . 4.2 . 4.2 . 4.2 . 4.2 . 4.2 . 4.2 . 4.2 . 4.2 . 4.2 . 4.2 . 4.2 . 4.2 . 4.2 . 4.2 . 4.2 . 4.2 . 4.2 . 4.2 . 4.2 . 4.2 . 4.2 . 4.2 . 4.2 . 4.2 . 4.2 . 4.2 . 4.2 . 4.2 . 4.2 . 4.2 . 4.2 . 4.2 . 4.2 . 4.2 . 4.2 . 4.2 . 4.2 . 4.2 . 4.2 . 4.2 . 4.2 . 4.2 . 4.2 . 4.2 . 4.2 . 4.2 . 4.2 . 4.2 . 4.2 . 4.2 . 4.2 . 4.2 . 4.2 . 4.2 . 4.2 . 4.2 . 4.2 . 4.2 . 4.2 . another 4.2 over 10. 7/10. Now, you can put all this in your Alex calculator, but I'm going to show you the way I do it. Nine-tenths. And then the last one is the same one as all the other even ones. All right. So all of the positive ones we've got 1, 3, 5, 7, 9. So we'll do it on the calculator real quick. 1 plus 3 plus 5 plus 7 plus 9. And that's our 5 positive numbers. So the expected value is going to be 25 over 10. Someone put everything over 10. And then the negative ones are just those 5 ones that are negative 4.2. So 4.2 times 5 gives us negative 21. Or it gives us 21. And we're going to subtract. And that gives us 4/10. And then we're going to pop that into the calculator and get the decimal. So what that is 40 cents. Since the positive one is smaller than the negative one, then that's why it comes out to 40 cents positive. So then we're going to put over here our expected value. It can be negative, but in this case it's positive. So $0.4, that's the same thing as 40 cents. So since it's positive, he can expect to gain money and he will win 40 cents. Just a word of caution here. If you come out with negative, you put the negative up here, but you don't put it here because the lose is your negative. All right. I know that this is, especially this one. Like I said, I should have done a smaller one so I'd have more room. But any questions about it? I'm going to do another one that's a little bit less complicated. But not all of them are 10. Like I said, this is 1 through 8. And I probably should have just went through and got one because I know there's one in here with 6. But most of them are 8 and 10. But there's a 6 in here somewhere, I'm sure. But yeah, there it is. But you got to go through a million of them. Anyway, what I'm going to do though for the last one is a business application. Same kind of idea. This one is not going to have but maybe 3 possibilities for outcomes. All right, so I'm going to erase that here. All right, so let's erase this. And this will be our last problem of the evening. The Brady and Matthew Camera Company has just come out with their newest professional quality digital camera, the ToughBix One. The camera is selling only through its new mobile app at a profit of $187. This purchase comes with a guarantee that, barring gross negligence, if the camera breaks in the first 2 years after purchase, Brady and Matthew will replace it free of charge. Replacing a camera this way costs $4,800. And here's now our different outcomes. Suppose for ToughBix One, there's a 4% chance that it will be replaced exactly once, and a 1% chance it will be replaced exactly twice. All right, let's make a little chart here. This one's going to only have 3. So we got no replace, one replace, and 2 replacements. All right, so our outcomes are going to be, that's what we call X, and then the probability of X. Now, the probabilities they give us here, so there's a 95% chance that it won't be replaced. Now, we got to write it as a decimal if this is going to work. This is why being able to go from percent and decimal and percent is important, because we can't really do calculations with the percents. So 95% is 0.95. Replaced exactly once is 0.04. That's 4% written as a decimal. And you can see, if you want to get back to it, you go 2 hops, multiply by 100, and you get the 95%. So this would be the 4%, and then this is the 1%. Now, if there are no replacements, then they're out nothing. Okay? But if they have to replace once, they're out $4,800. So you tell me, for the last little line there, if they have to replace it twice, then how much are they shelling out? $9,600, because it costs them $4,800. So there's 9,600. Let me see if I can fix that a little bit better. 9,600. So then we're just multiplying down X times probability of X. So this is 0, because 0 times anything is 0. So 9,600 times 0.0 is So 192. So then our expected value is equal to 0 plus 192 plus 96. Now what this means is, this means on the average, they're paying out $288 per camera. So there's the expected value is 288, but that's not what they asked. We got to go back over here and look at what they ask. If Brady and Matthew knows that it will sell many of these cameras, should expect to make or lose money. Are they going to make a profit? So remember, they're making $187 per camera. So if it's costing them $288 per camera, then they are losing $101 on each camera. So they can expect to lose $101 per camera in this scenario. That's how the expectation works. So if we'd come out, if it was a positive number, then it would be here, and then we'd put in the amount that they'd be making for each camera. But they're losing with each camera $101. And then if the price of this was the same, in other words, if they were both 187 or both 288, then that would be no profit. It would just be the breaking even. All right. So that's pretty much it. Anybody got any questions? Stick around. Otherwise, I'll see you Thursday. We're getting close to finishing this chapter up. Trying to go slow, but keep up with that. Please make sure you do that for me, the formative evaluation. It's got 7 questions in it. Please don't do that.
Good night.
Night, night.